Woo! All right. Cool. Well, thanks everyone for joining today. I don't have a whole lot of huge overall announcements at the moment. Tests, like Sean mentioned, is next week. So if you are going and attending, maybe drop a little line in general on Slack and we can all meet up at some point. Um, yeah. Anything from your end, Sean, before we start?
Um, can't think of anything at the moment. No. Uh,
Alrighty.
Looking forward to hearing this talk about LLMs though. I was uh I was just at the NASA S&D AI workshop all last week hearing about what a lot of people are doing with foundational models in various types of science. And then this is happening on Monday, so it's kind of a nice flow for me.
Indeed. Um, cool. Well, yeah, let's go ahead and get right into it then. Like Sean mentioned, we're talking about harnessing large language models to enable search and discovery and accelerate science and heliophysics. And we have a special guest here today to chat about that. Um, Koshal, is that how you pronounce your name?
Yeah,
Cool. Feel free to go ahead and take it away. If you have slides, you're free to present.
yeah, thank you so much for the opportunity to present to you guys. Yeah, pretty much today I just wanted to go over some research that I've been doing as an intern with NASA currently surrounding our work with large language models. So basically the way I capture what we're doing is harnessing large language models to enable search and discovery and accelerate sciences in heliophysics. So that's a lot of words. So I'll get into what exactly that means in specific.
Real quick before you move on, am I seeing
Yeah.
Ryan McGranahan there as one of your mentors?
Yeah, so Ryan McGranahan and Anthony Bonomo, those are the names of the two mentors I've worked with since the summer of 2023. Yeah.
Great. I know a lot of us here know at least Ryan. So
Yeah.
that's a cool connection there.
Yeah, most definitely. Yeah, just to provide a quick introduction. So I'm a sophomore currently at the University of Illinois, Urbana-Champaign. I'm currently studying computer science and philosophy, and like I just stated, I've been an intern with Ryan and Anthony since last summer, and our research has been ongoing work as part of the Heliophysics Digital Resource Library community, and this work has been centered around applying large language models for the purpose of relation extraction within the heliophysics domain. So, what exactly is the big idea influencing our research? So, scientific disciplines are focusing and utilizing increasingly complex sciences. We notice that information is becoming increasingly interconnected across scientific communities as a result of interdisciplinary collaboration and information integration. So, traditionally, information is represented in the form of scientific publications and literature, and we typically store these in databases. But as we soon discuss, this poses significant issues with search and discovery. So let's consider the use case where we have one publication. I can read over the publication, synthesize it, and tell you what the key concepts, important data points, and other relevant information are from this paper. However, in today's day and age, the sheer amount of generated information makes an approach such as manual synthesis simply unfeasible. So this raises the need for an automated way to process information and, more importantly, represent these insights. So our first problem comes with the way that we store information. Storing information as a entry or a paper in a database collection tells us nothing about the publication itself or how it's connected to other literature. It simply exists as an entity within a collection. Essentially, databases fail to capture the complexities and interconnected nature of data in today's day and age. Therefore, we propose a solution which will be able to capture these nuances. So we want a way to dynamically represent this information in the form of a knowledge graph. So what is a knowledge graph? Knowledge graph is a graph that consists of a key element called a semantic triple. So for those that don't know, just to give more background on it, it's a data unit consisting of three parts. So first, you have the subject entity, which shares a relation to the object entity. And this relation is represented in the form of a direct edge labeled the predicate. In the context of our research, each semantic triple represents important information about a synthesized paper. With knowledge graphs, we can easily understand key concepts and important data about scientific papers, as well as understand entities and their relations to one another. The ability to compute and represent exactly how entities within a paper are interconnected with one another is perhaps the biggest benefit to representing knowledge in this manner. So, traditionally, the process of curating an ontology, which is essentially a formal description of entities and their connections with one another, is an extremely challenging task within scientific domains. However, it's important to continue development of various ontologies and knowledge graphs, as many of the world's largest software are built off this technology. So having established that traditional approaches towards manual data synthesis and database storage are infeasible, we aim to automate this process of synthesizing data through utilizing what we term large language models. So what is a large language models? For those unaware, LLMs are pre-trained deep learning models which generate natural language. A very popular example of this would be ChatGPT, as we all know, which produces human-like text output to nearly any possible query. Now, this large language model technology, simply put, has exploded in popularity with unparalleled growth. As we see in the graph, ChatGPT's daily active user growth has grown at an exponential rate, far surpassing even the most popular platforms such as Instagram. The advent of this technology cannot be understated, and its instantaneous growth in popularity poses the question of, can we integrate this technology into the sciences? And if so, how can we do that? So it turns out we absolutely can. Highlighted on the slide are a couple amongst many more ways LLMs can be integrated into natural language processing tasks within the sciences. So specifically relevant for us are its capabilities to synthesize large batches of publications and output the semantic relations within them. Expanding upon how LLMs are applicable to our specific area of research, we notice that large language models have yet to be fully integrated into scientific domains, specifically with heliophysics specific tasks. Through this research, we aim to facilitate the continual integration of this technology into niche domain-specific scientific tasks. So I want to tie everything together. Up until now, I introduced a lot of different terminology, and it can seem a bit confusing. So how does everything relate to one another? So we can divide our research workflow into a few distinct parts. First, we utilize large language models to perform a task called relation extraction. So relation extraction refers to the process of extracting semantic relations from a text, essentially classifying this relationship between two entities. We query LLMs to perform relation extraction over a publication, and in doing so, the outputs we get from these queries are stored in the format of semantic triples. Now, with our batch of outputted semantic triples, we curate our knowledge graph, which is the final output of the pipeline that we create. Knowledge graphs and large language models both have their differing capabilities and exist in separate domains. What we're trying to understand is how they can connect, as too often we see them in a separate dichotomy. So now that we've established the necessary background information to our research, I want to give an overview for how the rest of the presentation will look. So first, I provide a high-level overview of the pipeline that we created, followed by an in-detail walkthrough of each phase of this pipeline. And then I want to discuss the data and insights we derived from testing out this pipeline, and conclude with implications of this work and future research plans. So starting with the very basic overview of our pipeline, you'll see that it works by taking in an input publication and outputs a knowledge graph representing the insights and data derived from this inputted publication. Expanding more in depth into how exactly our pipeline works, we develop a pre-processing phase that extracts the raw text from our publication, feeds this raw text in batches for each query to OpenAI's GPT-4 Turbo, and with the raw GPT-4 outputs for each query, we feed these outputs into our post-processing phase to procure our final list of processed semantic triples. Then, utilizing the D3JS framework, we produce our dynamic knowledge graph, which is outputted to the user. So the following is a worked example highlighting this process. So given this input publication, we produced a list of semantic relations. And with this semantic triple data, we produce our graph output. Now, the graph output, as we can see, can be very hard to understand how to use. The provided snippet of a semantic triple entity shows the type of data that we extract from the given input publication. Now, for a more in-depth explanation for how exactly all this is happening, as we established before, the pipeline is divided into two parts or scripts. Our first script focuses on generating the semantic triple outputs, with our second script processing these outputs to generate the graph. So the first script can be further divided into subparts. Our pre-processing phase at a high level entails receiving a publication as input and parsing it to retain the most information-dense and relevant information. We utilize libraries such as NLTK, PyMovPDF, and techniques such as text splitting to minimize context loss. Important to note is that we parse by paragraphs rather than store the entire publication text in one big chunk. Now, given our parsed paragraph list, we now query GPT-4 Turbo through iterating over our list, feeding the model the corresponding paragraph input with each step. Here, we utilize few-shot prompting to ensure our model is deterministic, and we essentially aim to reduce output variability throughout this process. This will greatly help us with the post-processing, as well as retaining as much relevant information as possible. So following our queries, we enter the final stage of this first script, which is the post-processing. Our post-processing stage utilizes spaCy for a variety of tasks, including fuzzy word match and lemmatization to remove duplicate and similar entities of semantic triples, and parts-of-speech tagging to tag and omit entities we deem lacking in relevant information. Once we have finished with this part of the post-processing, we enter script 2 of our pipeline. So script 2 consists of other post-processing stages, again, all with the aim of reducing ambiguity in our semantic triples. The first part of the script consists of what we term acronym expansion. What we discover is that across heliophysics publications, there are a plethora of acronyms mentioned within these texts. For readers unfamiliar with terminology in the heliophysics domain, these acronyms can be confusing to understand. Therefore, expanding them allows for a degree of increasing clarity. So how do we do this? We utilize the NASA HelioNode repository to produce a list of acronyms in their expanded forms, and we integrate this into our pipeline to expand any mentions of these acronyms in the text. The displayed example illustrates a use case for this functionality. So it's important to note that throughout this research, we aim to take advantage of existing manually curated knowledge representation artifacts and integrate them into this automated process. Now, across the 5 publications that we process, which I expand on later, we get the following data for what acronyms were mentioned and how many times they were expanded. As we can see, most of the processed acronyms are expanded once, with very few of them expanded several times. The next and final part of this pipeline's post-processing is what we term as synonym resolution. Oftentimes, many entities are synonymous and have negligible differences in their definitions. Considering these entities as separate would be disingenuous. Therefore, we believe linking synonymous entities to one central entity will increase the interconnectedness in our network representation, as well as increase clarity and remove clutter with our model data. To do this, we also utilize the NASA HelioNode repository to procure a list of synonymous words, each with the central word they are linked to. So the displayed snippet illustrates an example of this data. In this case, any mention of the synonyms to the right of the 19 would be replaced with the term scale. The left image shows a snippet of the central word entity we replace with the number of times that word is used for replacement. From the sparkline, we see that most of the entities that existed in these synonyms files were replaced one time, while fewer entities have far more synonyms that were linked to them. Finally, following the post-processing steps of our second script, we then take the list of semantic triples and curate our knowledge graph. To do this, we JSONify our data and utilize the D3JS framework to parse this data and produce an interactive dynamic graph. The following shows snippets of the graph that we produce over the 5 publications that we processed. As we can see, red nodes denote the subject entity, gray nodes denote the object entity, and the direct edge from red to gray node represents the predicate. The node sizes for subject entities are proportional to how many entities they have within the curated list of semantic triples. Essentially, the more semantic triples linked to a subject entity, the larger it will be represented on the graph. Now, expanding more into the different graph features, we believe that displaying different connections between subject entity nodes can offer great insight that might not otherwise be discovered. To do this, we use the following 2 metrics. First, an indirect connection occurs when 2 subject entities both share a connection with an object entity. In this case, we state that those 2 subject entities are indirectly connected and represent this connection through a blue edge. Additionally, we also compute the skip similarity in the following manner. If we have a subject node A with 2 subject nodes B and C as indirect connections, by definition of skip similarity, B and C now share a connection represented by a green line. So why are we doing this? Well, this technique of computing indirect connections and skip similarities is what we term as closing triangles. This is a very powerful technique that powers many real-world network-based algorithms for tasks such as recommendations, search engine optimization, and much more. So the previous slide showed a relatively simple use case of this feature. Oftentimes with academic papers, network representation becomes extremely convoluted. The above example highlights how connections and implicit relations between multiple entities start to get very convoluted in the context of these publications. Therefore, being able to establish these relations concretely is super important. Now, in testing our pipeline, we curated our knowledge graph over processing 5 specific publications focused on the magnetosphere-ionosphere coupling phenomena. We sourced these publications and reports from the NASA ADS library. The reason we choose a specific use case is for the following reason. This problem is traditionally a very difficult problem in heliophysics and needs help with understanding and synthesizing the material around it. Therefore, being able to run our pipeline on this use case provides a step towards understanding and producing insight with magnetosphere-ionosphere as a subtopic of heliophysics. So the following data from our curated graph shows the number of entities and semantic triples we curate for each paper. So surprisingly, we noticed that report length does not necessarily correlate with the number of triples that were generated. So this gives us insight into understanding where our post-processing methodologies should be tweaked, as in some use cases, the rule set we currently have for processing these outputs might be too strict in certain situations, such as the ion outflow paper. This is further seen in our degree distribution. A main weakness we notice in our network representation is that a majority of subject nodes have a degree of 1, meaning they only have one semantic triple that they are mentioned in. In a knowledge graph, we aim to display interconnected entities and their interactions and relations with one another. Standalone entities shows us that this goal is not really met and gives us additional insight that somewhere in producing the model outputs, we're not performing optimally. So, as mentioned before, this is what we mean by standalone entities. While we can derive information about single degree entities, we cannot derive much information with regards to how they relate to other entities within the network. Now, we derive a couple crucial key points from our degree distribution. First, nodes with higher degrees are important for study. This follows from the simple fact that the larger a node, the more connections its semantic triples are linked to it. Therefore, this offers easy insight for researchers to understand where the focus areas within a publication and corpus should be. Secondly, the existence of many single-degree nodes tells us that our approach needs to be scaled. In other words, it's simply inefficient and insufficient as well to test on one publication at a time. Rather, we need to scale our approach to thousands of papers. We also believe that our degree distribution will scale out as we scale our approach to processing far more papers than we are currently. Now, our current feature building includes the integration of the OpenAlex library. So for those unaware, OpenAlex is essentially a digital catalog consisting of a plethora of data regarding and relevant to research publications, such as authors, publishers, institutions, and more. So how do we utilize this tool? We notice that many of these subject entities in our outputs reference this data, such as authors, publications, locations, and whatnot. Unlike the nature of an entity that is very explicit in what it references and defines, entities that are more general or ambiguous tend to fall under these categories. In order to reduce ambiguity and derive information from this, we believe that parsing through OpenAlex's datasets will allow us to uncover information about these entities that would otherwise be unknown. For example, we have two subject entities of authors. From parsing the OpenAlex datasets for authors, we can derive the following information about this author: the institution they're affiliated with, how many citations they have on a per year basis, their different forms of identification, and much more. We believe this to be a very powerful tool that will bridge the gap between important chunks of data and information. So to summarize and conclude, what have we learned through this research? Simply put, the potential to apply LLMs in the tasks of synthesizing scientific information is unbounded, and this tool shows great promise. Through integrating large language models into this process, uncovering key information becomes a much more streamlined and efficient endeavor. Why is this? Well, with further refinement and development, our pipeline has the capabilities to process thousands of papers. Humans simply cannot keep up with this work rate. Additionally, we learned that we have to scale our approach to see where the knowledge graph stands for a true representation of the capabilities of our pipeline. In creating this pipeline itself, we established its nature of being a trial and error process. It's an open-ended question as to what pre- and post-processing techniques to utilize, along with other existing open source frameworks and libraries, to create the most accurate, precise performing pipeline. There's no right or wrong answer, it's simply what tools work best with each other. Lastly, even with something as powerful as LLMs, to make them meaningful to a domain, you have to have some format of knowledge representation. Without the artifacts we use, such as synonym resolution, we would not have been able to give the discovered entities their full meaning. So, in continuing research on this task, we aim to achieve the following. As stated before, scaling our approach is paramount and a big priority with this research. Secondly, we aim to continue the development of our network analysis and network representation capabilities in order to derive greater insight and expand search and discovery capabilities. One question we have is how would we be able to explore these options with PyHC? We also aim to make this available to the HelioNow repository and see potential for this pipeline to be used as a research artifact. We also see potential specifically for this to be utilized as an excellent reusable tool, such as a Python package. Additionally, we also ask the question of how exactly could this tool be used as an API potentially. Our general hope is that anyone working on research that can require or utilize such a tool to do so, because this can provide us with great feedback with our pipeline. So this concludes this seminar. So yeah, thank you so much for listening. And I guess I'll just open it to questions right now, and I'll be happy to answer.
Do we have any questions from the audience?
I've definitely got a few, if no one minds me going first. Yeah, first of all, awesome talk. Thanks for walking us through that. Um, so obviously the main thing that you're presenting here is the ability to make knowledge graphs from like scientific publications using an LLM. Yeah, and I want to know if you could just say a little bit more. I know you had the future work there at the end, but in what ways do you envision using these knowledge graphs now that you're sort of automating the ability to create them for any given paper?
Yeah, definitely. I think the main hope we have for this tool is that any researcher um, who needs to gain more information out of a publication or any set of literature uses these knowledge graphs as a sort of tool or like additional help to uncover like key points and relations. It's basically, we don't really see it as like something to replace reading over a paper and discovering how certain concepts and just things in general are related to one another. But that's what we envision for these knowledge graphs is somebody can run this pipeline, get the knowledge graph associated with it, and in addition to them reading over whatever it is they're reading over, they can look at the knowledge graph and be like, okay, so this is related to so and so. I wouldn't have been able to find that out if I just read through the paper itself. So it's just a way to like pick additional data points that you might potentially miss, if that kind of makes sense.
Yeah, it absolutely does. Um, it makes me think of a couple things, and I won't hog the floor, so I'll say this real quick and then let maybe someone else say something. But one is it does remind me of other work that I saw presented at the Dash conference last year. There was someone who was using LLMs to basically scrape, I forget what publication source it was, but there was like a few different like journals or something that they were watching for new papers, and every time one would come through, they would run an LLM on the paper to see if it was about, oh, they picked a specific mission. I want to say it was maybe MMS, but I don't remember. But someone was basically using an LLM to make like a detector of when someone published a paper on a specific topic. And your tool right there obviously goes like a step further from just saying yes or no with some confidence. We think this paper is about a specific subject. You actually break down like what the subjects and relationships are. So I wish I could come up with that person's name off the top of my head. It's not coming to me, but I'm seeing a lot of potential for collaboration and things like that. Maybe that's a comment. So one question I'll leave it with is I'm curious about how the resources have been, like the resource utilization as far as compute and money and stuff has been on your end. Because I saw that you're using GPT-4 Turbo, which is obviously the latest and the greatest LLM, but is obviously also the most like expensive. And I've run into cost issues trying to use that model for various projects. So how have you all been working with that?
Yeah, no, there's no denying that it's gonna cost money. Like even just we stuck to 5 publications and that had its significant expenses. So like if we do end up scaling this approach to 100 or 1,000 publications, it's going to be really like costly. And I mean, I assume that would just be an issue of like funding whoever has the money to give as part of like this research initiative. But yeah, I think cost is just something that's an inevitable. So unless like we figure out a way to work around that, I think it's just we're gonna have to bite the bullet on that.
Gotcha. And sorry, I know I said I'd cede the floor. One more because I have to. If you all actually do find the resources and the money and stuff to actually scale this up and start doing this for a bunch of papers, would the plan be to start to build out some kind of giant knowledge graph of just like an unfathomable amount of papers to have like some sort of super knowledge graph on all of the papers in the field, or what would be like sort of the end goal there?
Yeah, no, I think like that's like definitely a potential possibility of doing so. I think being able to have like a big central knowledge graph that could essentially represent like an entire topic or concept altogether could be pretty useful. So I think yeah, definitely that could be something we would do.
Nice. Well, we've got other hands now, so I will turn it over to one of you two, Jack or Jonathan, but you both seem to raise
I,
your hands at kind
I've
of the
got a
same
short
time.
comment that actually spins right off what you said, Sean. So I'll barge in. Um, it would be really cool um, if you were able to start pulling out information like what code was used, what data was used, that kind of thing, and be able to determine relationships between papers that way. Because um, I think one of the things we're pushing for on the open science side is moving away from papers as the sole means of communication. And I think the fact that you're doing this on a knowledge graph basis just opens up so much possibility.
Yeah, absolutely. 100% agree with that. I should make a note of that too. But yeah, I completely agree. I think there's a lot of potential to like just not just focusing on publications itself, but through other means. Yeah,
Yeah,
100%.
and even if you're starting with the publications, being able to crawl out of the publications and into the data they use, assuming it's cited properly, big assumption. But no, this is
Yeah,
this is really exciting.
100%.
Thanks.
Yeah, of course. Thank you.
Yeah, go ahead.
Yeah, so a couple of comments. So Anthony Bonomo gave that presentation last year at Dash, and the mission was Soho. So Anthony's also working on doing something related to what Jonathan was bringing up, of like extracting extra data. He's working with me and Brian and a couple of others on automatic detection and extraction of date ranges and instruments and observation modes from papers, so we can do that. So we can extract which data was analyzed and then provide links to those data. So that is ongoing. There's also 2 or 3 groups in Europe who are working along very similar lines that we've just started talking to. So Kashal, I think, your work is definitely cutting edge and is of interest to many, many people around the world. But I have a question. So there already is, and I may have missed it in your presentation, but there already is a knowledge graph implicit in almost all papers, and that's the citations in the paper. So how do they how do they match up, or do you use that information to help develop the knowledge graph?
Yeah, absolutely. I think that's what we're currently working on. Like you said, citations offer like a whole they're like a whole different world of information by themselves. So yeah, using the OpenAlex framework, we want to parse first to like get the list of the citations within the paper, run it through OpenAlex, see what information we can get from that. And yeah, that's going to be a big component of any other knowledge graphs we curate. I think citations, yeah, we definitely came to consensus that it shouldn't be ignored in our process of creating these knowledge graphs. So yeah, we're currently working on integrating that.
Okay, great. Thank you.
Hey, and Jack, if you could do at least me a favor and the name of the guy, yeah, you saw it right there. Jonathan beat you to it. Anthony, how do you pronounce his last name again?
You know, Mo,
Thank
he's working with Kashal, so
Good to have that name.
I think Julie and I piled on at the same time there. So
Cool. Any other questions? Comments?
I guess I can just ask, have you heard of the Dash conference before?
No, I have not actually. But
Yep.
it sounds very interesting. Yeah.
Not too surprised because we had the first one ever was just last year in October.
That's nice.
If you are looking for places to present your research, I actually just got word this morning that my session on AI and various things like that was accepted at Dash. So now there's officially going to be a session during this. This is like the data analysis and software for heliophysics conference. That's what Dash stands for. And I would personally love to hear an update about your work in October if you would be interested in coming to. Where are we having this, Julie? Where is Dash this year?
Dash this year is in Madrid, Spain.
Oh yeah, that's right. We're doing it abroad. So hey, if that's not a hindrance for you, I can say traveling to Madrid to present research stuff has been fun every time I've done it. There's a possibility to present remotely too if travel is difficult for you to arrange. But I think this
Chiming
is
in, Madrid, if you're going like East Coast to San Francisco for AGU, Madrid is only about $400 more in airfare and has a slightly lower cost for hotels and other stuff. So don't let the going to international throw you that far off. It's not a big multiplier.
Yeah, definitely. Yeah.
great.
No,
Well,
yeah. Sorry,
yeah,
were you saying?
we've got your contact info, obviously, from setting this up. So I will be in touch with you later about that.
Yeah, definitely. Super excited for that.
Sorry, Kat. Any other comments, thoughts, questions?
so I'm trying to find back the Soho large language model stuff, and I'm not. Was that a poster? Because I'm not finding it on the Dash site.
It was indeed a poster.
Ah. So I guess that we need to be looking at the Zenodo.
Yeah,
What
likely.
community? That's the term.
Yeah. Yeah, and I remember his poster was up during both Dash and IDEA. So I think it was formerly like a Dash poster, but yeah, don't quote me on that.
All right. Well, if there are no other thoughts or questions, we can go ahead and wrap a little early. Thanks again, Kushal, for coming and presenting. It's really cool to hear about the work you're doing, and love that you're working with Ryan, who's already done a lot of work and, the initial startup in this area. I'm really excited to see where this goes.
Yeah, definitely. It's a super exciting work, and yeah, thank you guys once again for having me. It was great.
Yeah, of course.
And before you get off the call, Julie, is there a website for Dash already? Is there like a link we can give this
Yeah.
man?
I think it's the same link as last time, or well, one second. Let me find it.
Yep.
I'll put it in the chat.
dash.heliophysics.net. Yes.
Yep.
Yep, it's the same as last time, and the old one's been archived off in another spot, which is great. And again, a reminder, we've got links of all the meetings of interest around here.
Mhm.
We do now. Thanks for that effort, John.
Tooting my own horn. Actually, less tooting my own horn and more about, hoping this is actually useful to people.
Yeah. But yeah, please go check out that Dash website there and bring it back to your people who can coordinate travel and that kind of stuff. Because this is definitely me formally inviting you to participate in that session, and then we can take it offline and email from there.
Yeah, for sure. I'll definitely check this out, and I'll let Ryan and Anthony know for sure.
Awesome.
Be great to also see Ryan there. Oh, speaking of your meeting calendar, John, based on our very official fruit poll that was in Slack general for the PyHC space during the spring meeting, it looks like we arrived at a consensus of November 12 to 14 for our fall 2024 meeting. So just keep that in mind all. Very early notice. I double checked. I didn't see any other huge meetings that week. It's going to be hybrid.
Awesome. We don't have anything else that in November, actually. So
Look at me picking a month that's not already got a meeting. I feel like that's pretty lucky in 2024.
yeah,
All right.
just if we're wrapping, is anybody planning on trying to go to SciPy? I was really surprised by the fact that they went from no information to, hey, we're open and abstracts are closed.
That I missed that one.
Yeah, it's like I was looking one day and there was no information up, and I was just kind of making guesses about when it might be, and I checked a few weeks later, and it was up and abstracts are closed. So for anybody else who wants to go to SciPy but not present, it's in Tacoma in July, and early bird registration closes the end of this month.
Well, thanks for the heads up. Someone's got to do it because apparently they aren't.
I'm not aware of anyone from SunPy who's going to the meeting.
Alrighty. Cool. Well, thanks everyone. See some of you all next week at TESS. To those who are not, I hope you might be able to view the eclipse somewhere. But if not, I'm sure we'll take a lot.